Are we ready?
Ooh.
Okay, hello.
Is it also coming up on the...
Yes.
Okay, starting finally.
There we go.
So yeah, welcome everyone here for the Ask Me Anything session with the Eternity Foundation core developer team. Yeah, we're happy to have you all here. Yeah, can you hear me?
Yep.
Yes.
Everything is good and we are live.
Yeah, so yeah, we would love to answer all your questions today, but first of all, I want to show you a brief overview of the roadmap for Q1 for 2022. And yeah, maybe we can go ahead. Also, happy to have you all here today. Dimitar, Wolf, Craig, Fabian, also Anita. Great to have you all here. And yeah, please give us a brief overview of the development roadmap for this quarter.
Okay, so I'll go first and I'll brief you with what is ahead of us. Basically, these are all the topics we are working on or we plan on working on. We haven't started on some of those. And I'll go one by one of each of those. The interesting thing would be the GUI and the advanced state channels, which Uf and Craig are going to focus especially on. What I'm going to be focusing on is our hyperchains alpha thing that is coming right after the corner. So let's start. Next slide, please. So we plan on releasing the hyperchains alpha. This is eternity node with a special config that enables special smart contract controlled consensus. Essentially, you can write any consensus you want to a smart contract, and it simply works out of the box. This is going to be our first step towards hyperchains implementation, and what is more is going to allow us to do well, it has different components really, and it's a tight consensus space where we'll be making conflicts to each other. So this is going to allow us to add more people to the effort, really. It's also going to allow us polishing the interface to that contract and see if we face any obstacles. And this is really agnostic to the hyperchains implementation itself. It all comes down to this smart contract controlled consensus, and this is work in progress still. It feels almost ready, but it's not. It has some missing details, but it's currently we can produce blocks by the correct miner, or rather leader, that is being collected by the smart contract depending on the smart contract implementation itself. We'll be working on some staking UI. So the plan is to slowly start onboarding users to our testnet and allow them to stake and to unstake and see how their stake grows with time, and how, if they support Alice or Bob, how this is going to impact Alice or Bob being elected as a leader. So this is going to impact the leader election itself. We're currently not working on connector to the Bitcoin or with any of its forks, nor on top of Eternity as a parent chain. This would be done only after we have something stable to be working on. The staking contract itself is almost done. It consists of two parts: delegated proof of stake part, which is ready, and leader election part, which is also ready, but those are split into different contracts. We will soon combine them into one. Next slide. We've been doing Roxdb database refactoring for quite some time, and this is going to allow us to do a lot of fancy stuff. The goal is to be able to do a garbage collection of the names, which takes a lot of space currently. Garbage collection of the contract states, which also takes a lot of space. The work there is almost done. Now we're doing the database migration process, which has a lot of pitfalls, but we're flattening those out. Eventually, it's going to get much faster. So this is going to impact the sync. Currently, our sync is currently limited mostly by the speed of applying database transactions. Or depending on your machine, that could be the disk, but usually it's database thing. Next slide. We're also working on a graphic launcher. It's really cool thing. It's a native Linux application that would allow you to download, to compile, set up a node, and run it. And there are a lot of more perks on the way, but Craig is going to be talking about those, so I'm not going to steal his light. So next slide. We're also working on the Rosetta API. We have a developer that is part-time on the project, and he's working on this when he has time for eternity. So not much details to share here. It's simply API implementation. We're also working on sync improvements. This is going to result in a much faster sync. Currently, the sync, depending on your network, your SSDs, and your CPU, and everything, takes days. We're doing, currently it feels more like a R&D project because we're still trying to grasp what we need, which would be the cornerstones, what would be an issue for us or not. But it's generally implementation of the Beam Sync protocol. It's going smooth, it takes time, it's really complex, and furthermore it has hyperchance complications that we'll be facing somewhere down the road. The thing with proof of work is that every block comes with a solution to the proof of work, but this is also the case with hyperchance. But in order for you to be able to prove that, you need the contract state on every key block. So we have to be syncing every key block down the sync process in order to prove that the key block. So we're syncing the smart contract state to be able to prove that the key block is valid. But not impossible, so we're moving there. We'll be showcasing state channels advanced features, but I will let Uf elaborate on that as well. We're making a Multi-Sig command line tool. Currently, the blockchain supports Multi-Sigs, and those work out of the box. They don't require hard fork, but you still have to provide the correct signature. And Hans had been doing a command line tool that allows us to do that. It's trustless, it encrypts the keys, and if you happen to forget them, it has a mnemonic phrase support. And other tasks we've put on the roadmap when we have time, because we're, as you can see, we're a small team and we're overloaded with work. But whenever, for example, the hyperchance alpha implementation currently is blocking the hyperchance alpha UI. And while doing that, we spend some time on Canary. Big refactoring is going on there. We found some bugs and those are fixed. Tainted accounts are down the line. Once the Roxdb refactoring is being done, we can start garbage collection of names, contracts, oracles, and even YAMLs. But all of those are really not that important. Our main focus currently is hyperchains Alpha. So that's our roadmap. I'll pass now. I don't know Greg, who wants to go next.
Great.
Yeah, I'll talk about the GUI thingy. Let's see. My turn to share. I'm just going to share my whole screen, so
No worries.
yeah, because it's like windows are going to pop up and stuff. So let's see here. Am I good to go? I think so.
Yep.
Okay, so the GUI launcher. Right now, it works on Linux. We've gotten it to work on OS 10 also, but the focus is not full cross-platform, compatibility just yet. So Linux is kind of the easiest playground for me to get it working, and then I'll focus on OS 10, BSD, and Windows and so on. Well, that doesn't tell you much, does it? So what the GUI does is that big enough to see?
Yep.
Okay, so this is like the root directory right now of this of the project. It's based on a toolkit called ZX, which lets you just dynamically launch Erlang projects on the fly, which makes development really nice. So I'm in the project directory right now, so I'll just run it and we'll see what it does. So is that readable? I hope it is.
I can read it.
Yeah,
Okay.
it's readable.
Okay, cool. So Configurator, this is still a work in progress a little bit because it's kind of ugly. The thing starts out with two default configurations for mainnet and testnet. And if you accidentally delete those, if they go away, it'll repopulate them. So it's not too bad. Disaster recovery is very easy. Nuke the directory and restart it. There's a configuration interface for this. This is not the easiest to navigate right now, so I need to put a little bit of work into that still. These are just debug messages for me as I write the navigator for it in the background, so don't worry about the text on the screen. Anyway, the whole idea with this is to make it possible to edit the configuration for a node or create new configurations that are, based on old ones or whatever, in a way that you can't screw up something trivial in YAML or JSON or make a syntax mistake and not realize what's going on until a bunch of weird stuff shows up in log files later. So that's the idea behind the configuration interface. It just needs a little bit more beautification to be more user-friendly. The internal parts of it, the checkers and all that stuff, that's kind of just the messy coding bit. The fun part about this is running a node. Of course, you can do. I missed my mark there. Okay, running a node from this, you pick a configuration that you want, and you just run it. That's it, and it's going to start. Again, we're going to have all this output in the background here. That's just because I'm showing all the log messages right now. So it's starting sync because it's built. If we were to just wipe it out as if it had never been run, let's see. So we're just going to nuke everything. There's no more. AL is completely gone. And if we wipe out the whole thing, okay, it's completely gone now. We're going to start. It builds itself. We decide to run a node. We're going to run a mainnet node, and it says, "Hey, you want to run a node? Great. Make sure this stuff is installed, and it'll generate this message based on your platform." So you would copy this and then paste it in to install all the dependencies, which we may make that into something that happens locally for you so that we could get a compilation that doesn't require any messing with the underlying system at all. That's something I would like to do. Anyway, once you have the dependencies, the package dependencies installed, it's going to clone the project, check out the correct bits that you need, and well, it's already done that now, so it's building. Like, this is it, it's building from source to the correct version to run with this version of Ale. The way that this gets, I'm going to be releasing this through the ZX kind of packager thing, and that will always keep this GUI up to date with the current release, and any given version of Ale will know what version of Eternity that it's supposed to check out and build. So that'll all just be taken care of. And that's that. That's kind of what the GUI does. There's a couple of grayed out buttons here. One of them is Developer Workbench. That's something that I'm very interested in personally. That will allow us to start a node in developer mode, dev mode, the dev mode plugin, where you split a snapshot of the chain, and then you can it gives you complete control over consensus. So you can just generate arbitrary key blocks and micro blocks as you go. Give you access to the compiler directly within the node instead of doing this call out across the network to get a compiler thing to run or whatever. Kind of give you a place that you can write Sophia code, compile it right then, check it for errors, deploy it, and then see exactly what's happening right there on your own system. Exactly what happened with the mechanics of your contract development. So I'm interested in that for myself because there's a whole bunch of things I want to write. So this toolkit is going to be fleshed out, as I encounter obvious features that we all kind of need quality of life improvements. I'll be adding ways to access those from the GUI. So that's the plan with that. It doesn't replace the it's not a replacement for the JavaScript stuff. It's not a replacement for the web side of any of this. It just allows us to have a graphical program that we can talk to the internals of a node directly instead of having to write some external abstract interface that may or may not be able to do what we want. So this is a kind of fun thing. You notice there's some graphs over here with the transaction pool graph, and it tells you what the height is and what the sync state is and the difficulty and the network peers and stuff. These will be changing and evolving a little bit as we go and decide what's useful to show, what's not useful to show, and so on. So anyway, that is the GUI. This is already actually not too far away from being finished, if Rox is built. So anyway, that's the GUI. If you have any questions about that, please feel free to ask. So that's all I've got on that. Who's next?
So I guess I'll.
Oh wait.
Okay.
Sure.
Do we want to take those questions now, or?
I guess let's first present what we're doing, and then we'll answer questions.
Okay.
Yeah, after the presentation.
Okay, so I can give a little. I will give a little presentation.
You're muted.
I'm muted?
I can hear you.
Yeah.
Yes, not muted.
Good. Okay, so the stuff I'm going to show now is actually didn't require any additional features on the chain, so this can actually be explored right now with the current functionality on the mainnet. I would recommend, for example, my Universe 1 presentation on state channels from Prague 2019. This is from that presentation, but just briefly, perhaps you know what eternity state channels do. They're a way to go offline with some tokens and in a one-to-one channel and progress through mutual signing, trustless, very quickly without fees. And compared to other state channel implementations, for example, on Ethereum, eternity state channels are actually first-class objects on the chain, and that makes a lot of things easier and cheaper and faster. And this has been working for quite some time. We can also load contracts in channels and make contract calls that are also co-signed. So essentially, you create an on-chain transaction, create channel, which creates a context on-chain. You can deposit and withdraw tokens. You can do snapshots, which can be useful if, for example, you go offline, but you want to make sure that the most recent state of the channel is captured. And if there are disputes, you can actually force a contract call on chain through the dispute protocol, which makes sure that you can actually progress to a valid state. So essentially, if this is the chain with the blocks here, you have a life cycle where you do you open the channel on the chain. You may do some on-chain updates of the channel. Otherwise, you don't touch the chain until it's time to close. And in practice, it will look like something like this. You have Alice and Bob who want to set up a channel, and they will each have a proxy inside the node, which we usually call the FSM. In this case, it's the Cheshire Cat. But anyway, Alice wants to send tokens to Bob. She sends a message to the proxy, and the proxy sends a message back to what's typically a JavaScript client, perhaps asking Alice to sign. Alice signs the transaction, sends it back. It's passed on to Bob, who co-signs, and this is forwarded back to Alice. And now both Alice and Bob have an updated state where the transaction has taken place. So this is the basic workflow. Now, performance-wise, what we've benchmarked in our test suites, now this is not exactly you could see this as numbers that exclude network delays and signing delays. But essentially on one channel, you can manage about 100 transactions per second, simple payment transactions. If you have concurrent channels on one node, you can handle several hundred transactions per second in total. On one channel, you can do about 25 contract calls per second. And we also have something called in-band messages. These are just generic messages you can send that don't require signing, and you can do thousands of those per second. So if multiple nodes in the network are running multiple channels, you can basically scale up to easily many thousands of transactions per second. And this capability exists today. So disadvantages is, for example, when you post the channel context on chain, as is typical when you want to put something on chain, you want to wait for confirmations. At a minimum, you need to wait for a microblock that contains the channel context. That's what would be our version of zero confirmation. That would come within a few seconds, typically less than 3 seconds. One new thing, if you compare to the Prague presentation, is that you can actually now, via the client interface, defer the confirmation wait. So you will get a message once the expected number of key blocks have piled on top of your context. But if you send a defer request, you can actually start transacting as soon as you have the microblock confirmation. So this allows you to get going quicker, and it's up to you how much you want to transact until you get a final confirmation. In many cases, this may be absolutely fine. But it still takes a little while, and it can be awkward to have to create a channel every time you want to do something. And the channels are very robust, so that you can essentially go offline and then recover the channel once it has been created. So it can go down and then you can get it back up very quickly. So the idea that I wanted to explore was that you could set up a permanent channel to a market. We call this an intermediary. So say that Alice and Bob are connected to the channel market run by Ingrid. They are sort of technically on separate state channels, but there is a technique called hashed time locks, HTLCs, which would allow you to relay payments or transactions across multiple state channels. So it would look something like this. Here is a state channel for between Alice and Ingrid, and here is a state channel between Alice and Bob. So Ingrid would keep some kind of registry so that she can find different state channels. So for example, if Alice says that she wants to send money to Bob's pub key, Ingrid would know which channel that corresponds to. So I have a test suite actually that does this. And it sends a generic message, very quick, lightweight, doesn't require signing or anything, where Alice requests a send transaction to Bob, and she will provide some unique ID and an amount that she wants to send. Alice will forward that to Bob, and Bob generates a secret and sends the public part of this, which is then called the hash lock. And this is forwarded back to Alice. Now, Alice makes a contract call on this channel, and this has to be co-signed by Alice. And it's essentially registering a new send operation to Bob with a certain amount and the fee that Ingrid perhaps requires. And then a timeout, number of key blocks that this request will be valid, and then the hash lock. Alice can actually, this money, the amount and the fee will be deposited in the contract, but Alice will not be able to withdraw because she doesn't know the secret part of the hash lock. So what she can do is she can forward the send request by making another contract call, new receive, from Alice with the amount, the time lock, and the hash lock. Bob can then take the secret, and so Bob passes this in the contract call. The interesting thing is, as soon as Bob makes the contract call, this is sent to Alice for co-signing. So then Alice will actually have the secret even before she signs it. This might seem like a security hole, but Bob can actually force progress this and receive the money. So this is not something that Alice can actually block. So, or Ingrid. Ingrid now knows the secret. So then she calls on the Alice chain a contract call where she can collect the collateral that she had to put up. So basically, when Alice posts an amount here, it's locked in the contract. And then Ingrid needs to lock that corresponding amount on the Bob contract. So Ingrid needs to have sufficient collateral to transfer this. But as soon as this closes, she gets the money back plus the fee. So that's basically how it works. There is a test contract. You have, there is a delay there. But on the bottom of the screen, you see a link to the entire channel contract. And so in the contract language, you perform all the necessary checks to make sure that it's that the right person calls the function, which this ensures that, for example, only if, for example, Alice creates a new send operation, only Bob can unlock it and things like that. So, and this seems to work. The test suite also verifies a bunch of error cases, timeouts, things like that. So in the test suite, one such payment takes about 15 milliseconds to complete. Now, even adding signing and network delays, my hope was that this would be fast enough so that you could essentially embed it into a button on a web page. And one use case that we were discussing, for example, in Prague was pay to read. Like you have a micro paywall, you go in, you look at an article, you read the intro, you send some money and get the next page, send some more money, get the next page, so on. And this could be fast enough that you could actually do that without noticeable delay. And from before, we have the AE channel service application, which is actually a server-side Elixir application built to service multiple state channels. It was actually built with this in mind, so it would actually be a very good foundation for our market hub. And another use case that I've been thinking about is that you could actually do a peer-to-peer trade using this pattern where you set up, you find an intermediary, or it could be a service that provides this function, and say I want to buy some Eternity tokens from Craig, but I don't really trust him, so we ask Dimitar to play intermediary, and so Craig posts his Eternity tokens in the send contract, and I transfer the requisite amount of euros via PayPal, say, and once Craig can show proof that they have that the money has been received, Ingrid can pass on the tokens to me. And this if you go through the scenarios with the different ways to, it becomes a little bit more difficult to cheat each other. And potentially you could also automate some of the, for example, detecting or recognizing a receipt or whatever, and automate some of this. But this is not something I've experimented with yet. So those were some use cases. So this could, I believe, be built right now. The contract that's in the repos could be a very good starting point for doing this. And the test suite in Erlang runs through the basic use cases. So that was basically what I was going to describe. So, and again, this does not require any new features in the mainnet. It could actually be done on the mainnet right now. Okay.
Excellent.
I think we're
Do
done
we have
with
any
the
more?
questions. Ooh, it's
Yeah.
stuck here. Maybe we can go to
Accumulating a few questions.
Yeah. I see the first two are regarding hyperchains, and the second two are regarding state channels. So, unless anyone objects, I will answer the first two and leave the third and fourth to.
Sure.
Okay.
Did you turn off the lights, Dimitar?
I have no lights at the moment. I can let me start the one. Feel free answering the third and fourth question while I do so.
So the question, can state channels only be used by two parties at the same time? Yes. State channels currently are only support two users in the same channel. Like I demonstrated, you could build a hub of channels that actually communicate with each other. But the main reason for not allowing more than two actors is basically that the dispute protocols become more complicated, and they're already fairly complicated. So we've thought that we'd keep them simple for now. So practical example use case of a state channel. So essentially, well, you could, we did demo earlier a simple casino game, which was a coin toss game. It was, that demo actually exists on GitHub with some instructions on how to run that. And one of the ideas there is essentially you set up a channel where you play some game. It could be a game implemented in a contract, and you can be betting and doing various things with and getting really good performance this way, and all the and then essentially you can top up the channel, and you can withdraw funds. So basically things like that, where you can, like, granted the aeternity state channel is pretty quick, so you can do on-chain transactions and you can get at least initial confirmation within seconds, but on a state channel you could actually transact much quicker than that and without fees, or the fees that you incur with the on-chain interactions are amortized across all the other transactions. So
Right. So that's that same question, right? With the what's the advantage over with state channel just over a transaction? From a vendor's perspective, it can also be good too because you can limit risk. So, for example, if you have a let's say that you're running a game or you have some game system and there's a in-game payment option, micropayments are enabled or loot boxes, whatever. Players might not want to expose their entire Eternity account to a spend transactions on a game that might have a digit off or something, right? So you could, when you load the state channel or when you top up the state channel, you can pick, okay, I'm going to put 1,000 AE in here and I can't overspend that within the state channel because that channel is capped at whatever the current balance within that channel is. So it gives the user and the vendor a good barrier because it's not like Visa where you can stop a payment because there's no real intermediary when you're doing on-chain transactions. So state channels kind of gives you a good barrier there as well, which also means that you can create like arbitration schemes that are faster, that don't have to run through a transaction or run specifically through a contract call. Because most arbitration schemes that are based on smart contracts are based on contracts. You can do something a little bit different that's way faster that you might like more based on state channels, because those can be the things that you write inside of a state channel can be arbitrarily fast too, or arbitrarily process heavy, because you're not being charged gas the same way that you would be on the main chain, that's a big difference too, because when you commit the state channel back to the main chain, it's all just a roll up. You don't have to go through verifying every single thing that happened in the state channel if you don't want to, which is a huge advantage to the whole network. Same thing with storage. The storage overhead of, everything that ever happened on the chain is on the chain forever, which means it only ever gets bigger. That storage problem is eventually going to have to be tackled in like a definitive way. And nobody's really looking at it seriously because they're scared of the problem. State channels is a way of kind of sidestepping that to a large degree by putting that state in a state channel, having an agreed commit back, and then that's it. Now you're just moving on. Yes. That's a really slick way of stepping away from the terror of the blockchain explosion problem, which is coming. Not to us too bad yet, but
it also gives you more privacy.
Yeah.
I could mention on the question number 6, if I read that as if you wanted to do a micropayment using state channels, there would be no advantage to doing that compared to doing it on chain, because even the simplest state channel involves 2 on-chain transactions, where you first open the channel, that's 1 on-chain transaction, then you can do the payment, and then you close it, and that's another on-chain transaction. So you actually double the amount of transactions compared to a simple spend. But if you would compare it to, say, your typical coffee card, where you top up and you could have a state channel, you could essentially have a permanent state channel from your phone to your particular coffee shop. And once you get into the store, you activate your state channel and you quickly co-sign, and then it's basically immediate payment with immediate confirmation, just like a typical coffee card that you probably already have, except it would, with this channel market structure, it could be universal. So you could use that same card for any service that exists on that market.
So
okay,
looks like we have a USSD question that I was kind of fiddling with in the YouTube chat earlier. USSD is not a specific structure that we're looking at making the first class object in the chain or in the protocol right now. One of the reasons that we wouldn't really need to is we can already put arbitrary data on the chain through transactions. So if the
I think the
USSDs
focus is when you don't have internet, without the internet
Right.
connection.
without, okay.
And
it-
we already have support for that, actually. State channels depend on you being online. So you can protect your own interest. But there is no problem of doing transactions completely off the grid, completely offline. What state channels need is two signatures. That's it. You compute a new state, and if both parties agree on the new state, like I'm giving you 5 coins, anything, I'm giving you a magic sword in our state channel game. Then if both parties agree to that this is the new state, this is the new state, then comes a question of trust. So if I don't have internet and I have a game with Ulf and Ulf has internet, he might try doing an on-chain dispute while I'm offline, and especially if he knows that I'm offline. But this is easily preventable as Eternity already has embedded in the protocol the functionality of delegates who can protect my interest and the ability of setting arbitrarily large frames for the dispute itself. So if Ulf goes to the chain trying to cheat me, and if our dispute is like measured in days, once I get home where I have internet connection, I certainly can protect my interest with regards of the dispute time frame. So this can already be implemented on top of Eternity. We've skipped the first two questions, and I don't know how to answer those. Let me read them out loud. Would anyone explain the flow on how hyperchains work with proof of work in selecting the miner to create the block? And the second one is, what is the place of Cuckoo cycle if hyperchance is used to randomly select miners? So first of all, in the context of hyperchance, there are no miners, there are only leaders. It's a hybrid approach between proof of work and proof of stake, but the leading one is proof of stake. So whenever there is a hybrid between proof of work and proof of stake, it's either proof of work with a proof of stake component or proof of stake with a proof of work component. And what hyperchains are is a proof of stake consensus with a really strong proof of work component. But this proof of work is not part of, it comes from another source, let's say the Bitcoin network or any network, or it could be Eternity network for that matter. The idea is that we have a parent chain and a child chain, and the parent chain is a proof of work network, and the child chain is reusing the proof of work of the parent chain. So whatever security has the parent chain, this is the child chain derives its security from that. What the child chain does is it puts, let's call it snapshots of the state on the parent chain. So if there is a reorganization on the parent chain, then this is going to propagate to the child chain. It's really important that the parent chain is proof of work, or as you can see, hyperchains can be embedded inside other hyperchains, but the most parent, the root of parent chains must be proof of work. This prevents long-range attacks. This prevents, well, a huge spectrum of problems that staking proof of stake consensuses have. So with regard to that, the proof of work is being used for serialization of events on the child chain, and it's being used as a source of entropy for the child chain. It could be Cuckoo. It could be Cuckoo cycle if the parent chain is, for example, Eternity. And it could be anything, really. So I think we should probably publish a document regarding how hyperchains work in practice. But this is not happening today. It's really a long subject.
Okay. So the second question, what is the place for Cuckoo cycle? So yes, if we're not doing proof of work on the child chain, we're not using Cuckoo cycle. It's a proof of work algorithm.
But the parent chain could be still Cuckoo. Like the parent chain could be current aeternity mainnet. So this is staying, right?
Yep. So going down the questions.
Yes.
SSD, we have.
The seventh one is, will it be possible to use generalized accounts within state channels? For example, for a temporary multi-sig. Yes, this is currently working. It's part of the protocol. It's already implemented and it's activated. It works. The thing is that whenever there is whenever you create a state channel, and if your account is already a generalized account, basically you're using a snapshot of your current contract state, and every subsequent state channel transaction, either online or offline, is being according to this snapshot. So yeah, this is working.
Will it be possible to move NFTs on state channels? Well, I assume yes, since NFTs are implemented in a contract. And
with a small remark, it will not be possible to move them out of a state channel or to transfer them to, well, it would be certainly possible to transfer them to another different state channel, but this is a whole different matter. I think the NFTs, their greatest strength is that they treat the blockchain as a ledger. And it's transparent, provable, and etc. While state channels are sort of private, and you lose that traceability. Yes, you can create an NFT in your state channel, and you can trade it with your other party as fast as you want to, but this is not reaching the blockchain. This is completely offline. So I'm not sure. Go for it.
yeah, so the next one, if the coffee shop closes the channel to collect payment.
Oh, that's not a. Is it a question?
It was a question,
Yeah, it's a
yes,
question.
from then the customers and shop will need to reopen a whole new channel, correct? Yeah, well, pretty much as with the coffee card, if the coffee shop server goes down, there won't be yeah, this is.
We can do intermediate commits back to the main chain, though, right?
You could. So one thing with these, if you wanted to use state channels for these types of payments, you would always want to have a fallback where you can just go to the chain. It would take a little bit longer, but so
yeah, the thing with the state channels is that it's kind of a built-in, better native version of kind of a layer 2 network in terms of getting around the storage and transaction bottlenecks. So imagine every coffee shop in the world. Let's just say that there's one of these wacky rules comes out that the only way to buy coffee in the world is with Eternity. Well, now you have a transaction, processing bottleneck that's pretty bad. But if the transactions all happened on state channels, the only commits back to the main chain are the rollups. If those were like, your monthly coffee bill or something like that, where the vendors collected and that's when the transactions kind of became real at that point. That state channel gets committed back to the chain. And those could be intermediate. I don't think it would be. Is that right, Ulf? You're the expert on these. If I have a state channel open, can I commit the intermediate state back without completely closing the channel? Does it have to be reopened?
You can. These are the snapshots.
Right. So Right. So the snapshot commit, that's not. So no, you don't have to close. You don't have to go to the trouble of totally closing out. All the money's back to you. All the money that's paid into the vendor is to them now, and then you're restarting from scratch a new state channel to carry on. That's not necessary.
That's correct. And you can suspend a state channel and then resume it. You can simply disconnect and reconnect, and it's still going to be there.
Right. So this is actually a really cool carry forward continuous account. Like if your relationship with a vendor, if you have lots of transactions per month with a vendor and you have a monthly roll up with the vendor, that's a tremendous savings in terms of transaction speed across the entire, just the whole system. Again, like I mean, it's kind of a better layer 2 that's just already built into Eternity that very few people have even tried to use, but it's an Uber feature. It's a super duper crazy, I can't believe people aren't talking about this all the time kind of feature. Because there's all this hype about all these other awful versions of something kind of sort of like that that's way less secure and way less well thought out. But like I've only been at Eternity for a year now, but when I found out about that, I just couldn't believe that it wasn't constantly being talked about. State channels are really, really freaking cool. I want to build a bunch of stuff with that myself. So anyway, state channels, really good idea.
So on question 9, I don't know if anyone feels.
No, I don't.
Keen on
The guys that are part of the... Okay, let me read the question. What is a good approach to have modifiers as in Solidity and Sophia, so no need to write require statements again and again and again? Please ask this question on the forum, and Hans is going to answer that. He is one of the big heads behind the design of the language.
So in general, I guess you would use the require statements in the entry points. And personally, I think that unless you have a huge amount of require statements that you need to go through, they actually serve as very useful documentation sitting right there. Well, matter of taste, perhaps. And like Dimitar said, please ask that question in the forum. Number 10, can one party close the state channel, collect payment, and run before a dispute is brought up? It's called solo close, actually, when you try to close the state channel unilaterally. And this can be useful sometimes. For example, if you decide that the other party is trying to cheat you, trust is there is no longer any trust, then you can solo close. What happens then is that a dispute period is started, which will go on for a number of blocks. What can, for example, happen is when with your solo close, you offer up a channel state to the chain. The chain obviously has no way of determining whether that is actually the final state. So that gives you an option to cheat. So then the other party can come in and actually offer a competing state, which is a later state. And if it's a cosigned state that is later than the one you posted, then the chain will accept that. And then you can go through that a number of volleys if you want to, until you either get to the actual latest state or the dispute period runs out. So anyway, there is a period where you can dispute the information provided by the other party. You can't refuse to close. If a unilateral close is posted, then the channel will close one way or another. So number 11, how state channels can work with micropayments for books, pay as you read. I'm trying to think of what I could add to what I described in the presentation. One thing about the generic messages in the channel is that you can send almost anything, or at least in chunks. So, for example, you could serve up a book in generic messages where you wait for payment to get the next page, and then you send a bit more text as generic messages, and then ask for more money. Number 12, what is the focus of development in 2022, and how can we help promote Eternity? Well, we presented the Q1 roadmap. It did involve a few other things that we want to keep on working on that are going to take longer than this quarter.